right, 4-3 in college algebra. Starting with nothing but notes. It's all front-loaded with notes, and we'll kind of come back to them. So I'll try to speed through this a little bit because they don't mean much until we get to some problems. But all the notes are at the front. Talking about inverse functions. What an inverse is when you do f of g of x, and you get x, and then if you do g of f of x, and you get back x, those guys are called inverses of each other. You've seen that before, where this symbol means the inverse of x. It's not said f to the negative 1. It's f inverse. And so when we do the composites, if you get x back both times, those are inverses of each other, and we'll label them like this. The weird thing about this lesson, though, is like they don't really talk about inverses. They talk about inverse functions. Because every relation has an inverse, and every function has an inverse. That inverse, though, may or may not be a function. Every relation has an inverse. Every function has an inverse. But that inverse may or may not be a function. So how do you tell? First, if you had a relation, you could make a mapping of it. And you want to see if it's what we call one-to-one. One-to-one means, first of all, this guy to be a function, every element in the domain maps to exactly one element in the range, right? One arrow coming off of all these guys, correct? Well, for it to be one-to-one, it's the other way around. There better only be one arrow pointing at these guys also. Isn't just one guy pointing to him, one guy pointing to him, one guy pointing to him, as opposed to, see in this, 1, 2, 3, even though this is a function right here because every element in the domain maps to exactly one element in the range, it's not one-to-one because don't both of those point to 3. One arrow is or two arrows is pointing to 3, bad deal. So if it's one-to-one, then that inverse will be a function. If a function is one-to-one, its inverse will be a function. That's if you had a mapping. How do you tell if you had a graph? Well, to be a function, you use the vertical line test to see if it's a function. To see if its inverse is a function, you use the horizontal line test. You see this guy right here. This is a horizontal line. Since it went through in more than one spot, that inverse is not a function right there. The original guy's a function. Doesn't the vertical line test get passed? Correct? If I'd actually be sketching vertical lines. But is the inverse a function? No, because this graph fails the horizontal line test. This guy is a function because he passes the vertical line test, but is his inverse a function? If you have a graph, use the horizontal line test. And if a horizontal line passes through the graph in more than one spot, that's a no. One spot, one spot, one spot. Right here looks critical. Like, how many spots? Well, if you'd zoom in a little further, you'd realize that it only touches it there in one spot also. One spot. This guy passes the vertical line test. He's a function. He passes the horizontal line test, which means his inverse is also a function. This is the same thing as before. The composites both equal x. That'll tell you if they're really functions. And then this four-step process to write that, we'll come back to it later. I just want you to realize you have the four-step process written right there in your notes. It's on the second page right here. When they ask you to use the four-step process to find an inverse, that's this guy right here. And then finally, they'll ask you a bunch of questions on My Math Lab. They'll say, which one of these four options, A, B, C, or D, are inverses of each other? And they'll just show you graphs. You'll have like a blue one and a pink one. Well, inverses reflect to each other over the line y equals x. Let me use a different color. This is the line y equals x. You see how those reflect to each other over the line y equals x. Cool. So inverses always reflect to each other over the line y equals x. So let's get to some questions finally. Determine if the function f defined by the arrow diagram, which is usually called a mapping, has an inverse. If it does, create an arrow diagram that defines the inverse. If not, explain why. We got to understand what they're saying. Because the real math teacher in me says everything has an inverse. When they're asking you if it has an inverse, they're asking you if it has an inverse function. So maybe make a note of that. Everything has an inverse. All you do is switch x and y around in your tables or your mappings or whatever. But they want to know if it's got an inverse function. And on a mapping, there's one way to tell if it's one-to-one. Here's the original mapping. Is it one-to-one? Meaning, each arrow is pointing to one thing, and then coming back, it's also going one way also. Is it a one-way street both times? This guy is one-to-one, right? So that means he does have it, the inverse is a function. Cool? What would it be? Everything in the range and the domain just switch. These two should switch places, these two should switch places, and etc. So let's find the multiple choice one of those where the domain and range switch place. So it should go 5682, 6704, switched around, correct? 5682, right? Isn't that all of the range from before? And then 6704, correct? Would you agree that this would be the inverse right here, choice A? Because x and y switch places in inverse equations. Lost the sauce? Determine if the function is defined by ordered pairs has an inverse that's also a function. If so, find the inverse. When they give you a relation is just a set of ordered pairs, make a little mapping of it. Here's your domain, here's your range. Make a little mapping. All the domains are your x values, 5, 4, 3, 6. Don't put anybody more than once. All your ranges are your y values. Don't put anybody more than once. 2, 1, 7, 2. I don't want to put him more than once. Then map them. 5 maps to 2 based on that ordered pair. 5 and 2 are partners. Right? 4 and 1. 3 and 7. 6 and 2. Cool? Is the inverse of this guy going to be a function? How do you know? This should be one-to-one. Is he one-to-one? No. So we'll say the inverse is not a function. You could actually tell that without making a mapping. I'm just a fan of making a mapping because that's the way most of the problems are typed at. But you can say, all right, I can see if it's a function if any x's repeat. Were there any x's that repeated? Yes or no? That's a function. I can see if it's one-to-one if any y's repeat. 2, 1, 7, 2. Did any y's repeat? Didn't 2 repeat? Right? So I could tell you he's not one-to-one. Right? You get all different y values every time, all different x values every time. Making a mapping, I'll have you do that on the test. So we might as well do that here also. Again, another relation, same question. First, make me a baby mapping. Always put a D in an R. Two, 3, 4, 5. And then 8, 9, 10, 11. I can tell already that it's going to be one-to-one. I had no x repeaters. I had no y repeaters. So this is one-to-one. They are asking us for the inverse of this relation. So since this guy was called F, whatever letter they use, they can use a G, they can use an H, or whatever. Use that same letter again, but put the -1 up there. That's F inverse will be this. You write another relation. And what do? You switch x and y around. So if this first guy is 2, 8, what's the inverse point of that going to be? 8, 2, comma, 9, 3, 10, 4, good buddy, and 11, 5. And then close your bracket up. Sorry, I didn't have enough room to write that. Try to write it lengthwise if you got the room. But the inverse of that, you switch x and y around. Again, like I said, every relation has an inverse. You can always switch x and y around. The question that they're asking us, is that inverse a function? It is when this guy is one-to-one. The inverse will be a function. Sweet! If f of x is this and g of x is that, what is f of g of x and g of f of x? So let's do a little bit of work. I don't like the parentheses stuff. I usually like the little composite symbol. I don't care what you write. But I'm going to find f of g of x first. F of g of x, which guy do I start with, f or g? G goes into f. So this thing is going into the f function wherever there's an x. Right? So I will have 4 times x plus 1 all over 4 minus 1. Sweet? times 4 and divide by 4. That makes things pretty. You've got x plus 1 minus 1, which is really how much? X. Ooh! Yay, I got x back. Then, let's see if g of f of x. Let's see what that guy is. They were asking us to find both. So now it's the reverse effect. I put this guy, f, goes into g wherever there's an x. So I will really have 4x minus 1 plus 1 all over 4. And wherever there was an x, I put f of x into that guy. There's no number outside the parentheses that I need to distribute to. This is just 4x minus 1 plus 1, which is plain old 4x over 4, which actually simplifies to be what? X. They want to know if they're inverses of each other. When you do the composite, f of g of x, you get back x. Then you do g of f of x, and you get back x. That means that they are inverses of each other. So, yes. F of g of x equals g of f of x, which equals x. Got to get x both times. Try that again. First guy, f of g of x. Put g in for x into the f function 3 times x over 3. So far, so good to see if they're inverses of each other. I got x back. G of f of x, f goes into g. You'll get 3x over 3, which is x. Are they inverses of each other? Yes! Try that on 6. I guess we'll do this together. Things are getting nasty. Notice they didn't tell me to find f of g of x and g of f of x. They didn't tell me to do that. All they're asking me is, are they inverses of each other? You with me on that? So what you'll do is you'll find f of g of x and see if it's x. And if it is, then you'll keep moving on and do g of f of x and see if it's x. And then if you get x back both times, you got a winner. But let's say I find f of g of x and it doesn't turn out to be x. Do I have to go any further? There's no need to, right? They didn't say find them both. They just want to know, hey, dude, are they inverses? So I'm a believer of always starting that way. F of g of x. Doesn't g go into f? You with me on that? So that means that the cube root of x minus 1 goes in for x. Then that has to get cubed. And then you still have the plus 1. I took this dude, put him in for x right there. So far, so good. Cubed and cube root cancel, right? So you're left with x minus 1 plus 1, which is x. I still don't know if they're inverses yet, but I'm halfway there. Right? So far, so good. I must keep going. Now I need to see if g of f of x also equals x. So this guy goes in for x right here. Cube root of x cubed plus 1 minus 1. With me on subbing in. Got to do what's underneath the radical first. That's a grouping symbol. Like terms. What's plus 1 and minus 1? So you got the cube root of x cubed. What's the cube root of x cubed turn out to be, baby? X. Are they inverses of each other? C. Got x back both times. Next guy. Are they inverses? F of g of x. Take g, put him in for x. Interesting. check your substitution with mine. The green thing is the g function. I put him in for x. With me on that? So, I got to take this whole quantity and cube it. Right? I got to take this times itself 3 times in a row. Do you think we're getting x back? Yes or no? Cube root of this, like when you would take x plus 2, quantity cubed. Remember how you do x plus 2 times x plus 2 times x plus 2. Right? You have to take it times itself 3 times in a row. Do you feel that you will get an x back when you do that? Do you know any kind of rules of like how there's going to be some cube root of x's in there because you got to take the first term times the last term for sure, and you'll get like -2 cube roots of this, that, or the other? There is absolutely, positively no way that that's turning out to equal x. Absolutely no way. Are they inverses of each other? Yes or no? So I didn't even do the work. I used previous math knowledge to say, absolutely, when you take this quantity cubed, I will not just get an x back. There's no way that these 3 things times each other will all cancel each other out and I'll be left with 1x. I mean, just think about if you did something simpler. You know, this is, you got to FOIL these, so x squared plus 4x plus x, then times this, x plus 2, you're going to get an x cubed in there. There will also be some x squareds in there. There will also be some x to the first in there. So like maybe this will go away in one of those terms. The cubed and the cube root will cancel out, but then you'll get some 2/3 powers, some 1/3 power. Ain't going to happen. Is the function 1 to 1? What would you do? Graph it. Graph it. So let's do that. X minus 3 as a quantity to the 4th power. Standard window looks like this. Here's my rough sketch. It's what I like to see, so I put that there. Make your axes. Rough sketch. Is he 1 to 1? Again, all the notes are at the beginning of this worksheet. This is a graph, not a mapping. How do you know if a graph is 1 to 1? Passes the horizontal line test. This is a function because it passes the vertical line test. Is it 1 to 1? Does it pass the horizontal line test? So, no, the graph fails the HLT, horizontal line test. Make a graph of stuff when it's not a relation. A relation is just a set of ordered pairs, like this ordered pair, that ordered pair, make a mapping. This is a function, right? Make a graph of him. So, is this a function or is this an ordered relation? Function or relation? I mean, yeah, it says it's a function, but is it an actual continuous guy with an equation, or is it just a set of ordered pairs? So you can't graph this, right? I mean, it's like you're not going to punch it in your calculator and see if it passes the horizontal line test. You could plot all those points. I don't want to do that. I'm going to make a mapping instead. 1, 2, 3, 4 for a domain. 5, 6, 7, 5. Shouldn't list anything twice. I pretty much am done, but before I even put the arrows, is he 1 to 1 is what they're asking. Is he 1 to 1? Yes or no? So no. There's the 4-step process that was previously on your second page. They want you to find the inverse of this guy. So here's the function. They want me to write the equation of its inverse. So first step, change f of x to y. That's step 1. Replace f of x with a y. Cool? Number 1. Step 2, switch x and y around. This is the true inverse step right here. Inverses are reflections over y equals x, so switch x and y around is step 2. Where there was an x, I put a y with it. Where there was a y, I put an x with it. Everyone cool with what I did? Switch x and y around. Step 3, solve for y. What would I do to solve for y? I would subtract 1 from both sides. Then I would divide all terms by 4. Cool. Step 4, change y to f inverse. And I'm also going to do a little symmetric property. I'm going to say f inverse of x equals 1/4 x minus 1/4. 4 steps. Number 1, change f of x to y. Number 2, switch x and y around. Number 3, solve for y. Number 4, change the y to f inverse. That's what we did. We wrote the equation of the inverse. If I graph him, and I graph him, they would be reflections of each other over the line y equals x. Because that's what we did. We let y equal x in this step right here. We let y equal x. Let's do it again. Step 1, change f of x to y. 2. Then step 2 is to do what? Switch x and y around. You all down with that? Step 3, solve for y. Ooh. This is a divide by y. How can I get rid of divide by y? Multiply every term times y. That's what I do. And I get xy equals 1. You down with that move? Right? Multiply both sides by y. Then what would I do to get y all by itself? Divide by x. Cool. Then, step 4, switch y to f inverse. Notice anything cool? They are inverses of each other. It's a hyperbola, correct? Here's the line y equals x. Does it reflect to itself over the line y equals x? It's its own inverse. Hey, buddy. It's its own inverse right there. Nobody died if you're watching this on the video. 12. F of x equals 4x squared for x greater than or equal to 0. Let's kind of understand why they did this. Let's preview. No calculator. Do you know what this looks like if we graphed it? It's a parabola that opens which way? Up. It would be like so. Why did they say x has to be greater than or equal to 0? If they said that, then if this is an eraser, wouldn't all of this stuff go away? X has to be greater than or equal to 0. Why did they do that? Tell me about the red thing. 1 to 1. Tell me about the red thing and it being 1 to 1. Is it 1 to 1? Why isn't the red thing 1 to 1? It does not pass the horizontal line test. But if I restrict the domain and say, go away, that part is that red thing that's left over, 1 to 1. So now the equation of its inverse will also be a function. Originally, we could still write the inverse as equation. It won't be a function at all. But they say, hey, let's do some calculating. Let's just like say, let's make this part of it only. Restrict the domain. So it'll just come into play later. Same 4 steps. Uno. Switch f of x to y. Cool with that? Step 2. Switch x and y around. Yes? Step 3, solve for y. What would be our first move in solving for y? Get y squared all by itself is what we want to do. What will be our first move? Divide by 4. So x over 4 equals y squared. Y'all down with that? Now that y squared is all by itself, can't I square root him? So that would be y equals, if I square root both sides, right? Y equals, oh boy, plus or minus. Is x a perfect square? Yes or no? Nope, so he's going to be a square root of x. Is 4 a perfect square? Yes or no? So that's going to become a 2. And there's your plus or minus. But wait a minute. Wait a minute. Do we need the plus or minus? Does the minus even happen? Because we restricted the domain to where x's are only positive in the first place, so the plus or minus does not need to exist because we didn't count them in the first place because x's are supposed to be bigger than 0. So no dice. That's step 3. Step 4, switch y to f inverse. And if I graphed him, he would look like this. Ooh. You see that those reflect to each other over the line y equals x. Yeah. One last one. This one, bring back some precious memories. Precious memories. What? Why? Switch f of x to y. What's step 2 in the inverse equation writing process? The true inverse step. This is where they are now. This red thing is the inverse equation. It's just not the way we like it. We got to get y all by itself. So my next move is to solve for y. First move, add 1. Yeah. Next move, divide by 2. Right? There's many ways to divide by 2. I'm going to make it easier on myself and do it all over. I'm going to say y cubed equals x plus 1 all over 2. Instead of 1/2 x plus 1/2. It really means no difference, but you'll see why I'd like to do that here in a second, because there's one more move to get y all by itself. This is where precious memories come in. What do we still got to do to get rid of a cube? Cube root. So, cube root of x plus 1 over 2 equals y. Oh, no. Can't have a fraction underneath a radical. So we need to simplify this radical. All right, let's give ourselves some more room here. Y will equal, I'm also switching sides right away, cube root of the numerator, my pen would work, over cube root of the denominator. All I did was split it up into 2 radicals, radical upstairs, radical downstairs. Remember, what I need is to get me a perfect cube down here in the denominator. Luckily, we just refreshed our memories of what perfect cubes were. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and etc. I need the number underneath here to become a perfect cube. So what I want to do is I'm going to set it up as a cube root of something over a cube root of something, rationalizing the denominator. I don't know what the number I'm going to put under there is yet, but I know I got to make this number 1. For example, cube root of 7 over cube root of 7. Isn't this really the number 1 right here? It's the same thing on top of itself. You with me? They divide out to be 1. You can multiply radicals together. Cube root of 2 times cube root of, let's say, cube root of 3. That would give you the cube root of 6, right? You can still multiply. Cube root of 2 times the cube root of 7 is the cube root of 14. You with me on that? You're just multiplying the numbers underneath there. What I'd really love to happen, though, is the cube root of 2 times the cube root of blank to come out to be this number underneath here, a perfect cube. I would love for that to happen. So 2 times what would give me a nice, neat, perfect cube underneath here? 4. Y'all down with that? I wanted to put a 4 underneath that cube root symbol because the cube root of 2 times the cube root of 4 will turn out to be the cube root of 8. You with me on that? So, let me erase all this nonsense for a second and give myself more room. La, 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 la. This guy is going to come down here to be, I know I got cube root of 8 in the denominator, and this is the cube root of x plus 1 times the cube root of 4. It's still a cube root of 4 times x plus 1 as a quantity. Let me show you that. Didn't you take 2 times 4 right here to get the 8? Well, you better take 4 times x plus 1 right here to get that. You all down with that? What's so great about this, though? Why did we do that? Because of this. What is the cube root of 8? It is 2. So you get the cube root of 4x plus 4 over 2. Where did the 4x plus 4 come from? I distributed that 4 through the parentheses right there. These do not cancel. This 4, 4, and 2 cannot cancel because this isn't a 4 and this isn't a 4. It's a cube root of 4 and it's a cube root of 4, and they are not multiples of 2 by any which way. So F inverse equals, woo, fun, fun, fun. More practice. Let's just say I had 7 times the cube root of 9. All right? I need to simplify this by rationalizing the denominator. Since this is a cube root down here, cube root of something over cube root of something. I need to put something in here that makes 9 times whatever that is turn out to be a perfect cube. What are perfect cubes? 1, 8, 27, 64, etc. Which one of these guys is divisible by 9? 27 is. So what do I need to put in there to make that turn out to be a 27? A 3. So this is 7 cube roots of 3 over the cube root of 27, which is really 7 cube roots of 3 over 3. What's so great about that? Now it doesn't have a radical in the denominator, because it's bad to have a radical in the denominator. Last one. Read it. Don't make these any harder than they have to be. Here's a function, man's shoe size, x. So x is their U.S. foot size. Right? To change it to continental size, which apparently is something overseas or whatever, continental size of your shoe, would be this function. Take your shoe size here in America and add 34.5 to it. Cool? They say find a function that'll convert continental to U.S. size. So if your U.S. shoe size is x, you've got to add 34.5 to it to get your continental size. If I tell you the continental size, how do you figure out the U.S. size? Subtract. So T inverse will be whatever your U.S., whatever that size is, minus 34.5. Now x is the continental size, and T inverse of x is the U.S. size. Those are inverses of each other. Like, hey, if you got to add 34.5 to get the continental, to go the other way around, you would subtract 34.5. Cool? Use the inverse function to find the U.S. size if the continental shoe is 43. So let's kind of go back up here and redefine stuff. Up here, x was your U.S. size. Right? But in your inverse function, since you switched x and y around, x now represents the continental size. You with me on that? We switched. We took an inverse, right? So since x was originally the U.S. size and we did an inverse, x is no longer the U.S. size. It's the continental size. It says use the inverse function, which is this guy, to find a U.S. size if the continental size is 43. Where should the 43 get subbed into? Green spot or blue spot? This is the continental shoe size. Where should it go in? Green or blue? Right? Cool. Goes in for blue, right? Continental size, that's what x stands for. So 43 equals 43 minus 34.5. I hope you know enough common sense about U.S. shoe sizes that if you got a size 70 shoe in the U.S., that you are the Jolly Green Giant. What did you get when you take 43 minus that? 8.5. You're an 8.5. Sounds about right.